Alright, well, let's see how this works. Cosecant is 1 over sine. Cosecant of 0, that's 1 over 0, which is infinity, minus cotan of 0 is infinity. Infinity minus infinity is a problem. The way this works, you would try to factor out the factor that's making a 0 in the denominator. See if you could cancel it out. If it is a fraction, well, this is not a fraction, but I could write it as a fraction. I'm trying to manipulate this to make it 0 times infinity or infinity times 0 and manipulate it accordingly. But if I happen to see a fraction, then the easy way out is just to get a common denominator. Most of the time that does the trick. So if I look at this, I'm sorry, that's sine of x. I notice in this case they both have the same denominator. And do you notice what I just did now? If I put a 0, 1 minus 1 is 0 over 0. It manipulated by itself by L'Hopital, limit as x approaches 0 of derivative of the top is negative, positive the sine of x. Denominator is cosine of x. If you throw 0 in, you'll get 0 over 1, which is 0. So in this case, infinity minus infinity happen to be 0. I'm going to give an example to really clarify that part. If I look at number 54, 1 over 0 is infinity. And 1 over inverse tan of 0 is 0. That's also infinity. This is another special case. So here what I'll do, I'll get a common denominator as well. Since this is already fractions, the LCD is x inverse tangent of x. That will be inverse tangent of x minus x. That's the limit as x approaches 0 from the right. And let's see, if I put a 0 in there, the denominator is 0. The top is 0 minus 0, which is 0 by L'Hopital. Derivative of the top is 1 over 1 plus x squared minus 1 over product rule. 1 times inverse tangent of x plus x times 1 over 1 plus x squared. This is the limit as x approaches 0 from the right. The LCD is 1 plus x squared. Clear the fractions. That is 1 plus x squared inverse tangent of x plus x. And that is 1 minus 1 plus x squared. So altogether, I'm looking at the limit as x approaches 0 from the right. 1 minus 1 is 0. That's negative x squared divided by 1 plus x squared inverse tangent of x plus x. If I throw 0 in, I'll get 0 over 0 again. L'Hopital again. Limit as x approaches 0 from the right. Derivative of the top is negative 2x. Derivative of the denominator, the product rule. 2x times inverse tangent of x plus 1 plus x squared times 1 over 1 plus x squared plus 1. So this is the limit as x approaches 0 from the right of negative 2x over twice x inverse tangent of x plus 1 plus 1. If I throw 0 in, I'll get 0 over 2, which is 0. So 3 cases in which we're dealing with infinity minus infinity, you guys. The first 2 to shed some light on this, so you know we're really getting more comfortable with this. This is infinity minus infinity. When I say infinity, I really don't mean infinity. I mean as x approaches infinity, that value is approaching infinity. This is infinity minus infinity, but I notice here that if I factor an x out, that will be 1 minus x. This would be positive infinity, and this would be a negative infinity. And I know positive times a negative would be negative infinity. The reason for that, x squared is going to dominate over x, so this entire function is going to behave like negative x squared, but this is how you show it. What if I swap those? What if I made it x squared minus x or x minus x cubed? That's not what I meant. Let's go the other way around. Let's make this x squared minus x. Well, the same deal. This is infinity minus infinity. The way it works, I'll factor an x out. This is approaching infinity, and this is approaching infinity. So that's actually infinity. And again here, x squared is dominating over x, and that's why this is going to behave like x squared. And this is infinity minus infinity. But if I simplify, that's 0, and the limit of a constant is the constant. Since those are canceling out, you're left with a constant. And here, I do know that exponential is going to dominate over x. So I do know this limit is going to be negative infinity, but I have to show it. How do you show it? You take the limit as x approaches infinity, you factor an x out, and you get 1 minus e to the x over x. Now, I know that this approaches infinity. That's simple. I need to figure out what this approaches. So I'll go on the side and I say, let me take the limit as x approaches infinity of e to the x over x. That's infinity over infinity. This is the limit as x approaches infinity by L'Hopital, e to the x over 1. Well, that's infinity. Well, look at it. If I take infinity times a negative infinity, wouldn't that be negative infinity? So this approaches negative infinity. This approaches infinity, and therefore that's negative infinity. That's how you would show it. And one more case on infinity minus infinity before we move to the last phase of this section, an extremely important section. If I put 1 in there, I do get 0. Natural log of 0 from the right is really infinity. If I put a 1 in there, I get a 0. Natural log of 0 from the right is infinity. But with logs, it's very simple to play with, because I know one of the properties of logs. I can combine the two logs into 1. And I could say that's natural log of the limit as x approaches 1 from the right. Where did 7 come from? You guys gotta be careful. And I could say by L'Hopital, that's the limit as x approaches 1 from the right, because that is 0 over 0. That's gonna be 7x to the 6 over 5x to the 4th. This cancels with 2 of those, and I'm looking at natural log of the limit as x approaches 1 of 7x over 5, and that would be natural log, and if I plug 1 in, I'll get 7/5. Okay, here we're looking at a quantity raised to a power. There are a couple of ways you could do this. The book really takes e to the natural log of the tangent of 2x to the x. That's really how to proceed with that. I'll do this problem this way. I'll say this is e limit as x approaches 0 from the right of e to the natural log of the tangent of 2x to the x. Property of logs, you could move that up, and you could say that's e to the limit as x approaches 0 from the right of x natural log of the tangent of 2x. And now if you put 0 in there, you will get 0, and this will approach 0, and natural log of 0 is infinity, so that's actually e to the limit as x approaches 0 from the right of natural log of tangent of 2x over 1 over x. Remember, you never move a log or an inverse per function. So this becomes approaching 0, and this approaches infinity. Plus or minus makes no difference. 1 over 0 is infinity. So by L'Hopital, e to the limit as x approaches 0 from the right, derivative of the top is 1 over the tangent of 2x times secant squared of 2x, and derivative 1 over x is negative 1 over x squared. So this is e to the limit as x approaches 0 from the right, and let me see what that is. This would be a cotan, so this is cosine of 2x over sine of 2x. This is 1 over cosine of 2x, and all of this is multiplied by the reciprocal of this, negative x squared. So this cancels with one of those, and I'm looking at e to the limit as x approaches 0 from the right, and let me see, of negative x squared over, now, the sine of 2x, cosine of 2x. If I multiply that by a 2 and divide that by a 2, wouldn't this become the sine of 4x divided by 2? Of course, you could leave it like that and use the product rule. It's a lot longer. That will work as well. Or you know what? Maybe that's what I should do. We'll do that in section 7.2. For now, let's leave it as is. Cosine of 2x, sine of 2x. So now, if you put 0 in, you do get 0 over 0 as well by L'Hopital, e to the limit as x approaches 0 from the right. Derivative of the top is negative 2x. Derivative of the bottom is the product rule. Derivative of cosine, negative the sine of 2x times 2 times sine of 2x plus cosine of 2x times derivative of sine of 2x is cosine of 2x times 2. And now, if you let x equal 0, you will get 0 over 0 plus 2, which equal e to the 0, which is a 1. There. Now, this is one way the book does. Anytime you see a power, they write it as, so if they have a to the x, they write that as e to the natural log of a to the x. There is another way, I think it looks simpler, but it's up to you, whatever you want. So I'm looking at this problem, and I notice this problem has the same thing. This is actually, as x approaches infinity, this is infinity raised, remember, this is natural log divided by 1 plus x. As x approaches infinity, this would approach 0. Again, a power. The way I would do it, I would say, well, let's take natural log of both sides. Natural log, I'll say let this be y, call this y equal that limit, and take natural log of both sides. I think that looks simpler, but that's only me though. You could, of course, use the book's method and carry the e. Now, by properties of logs, natural log of y equals, and the limit as x approaches infinity of natural log of x to the natural log of 2 over 1 plus natural log of x. One of the properties of logs, you move this up front. So natural log of y equal the limit as x approaches infinity of natural log of 2 over 1 plus natural log of x times natural log of x. I have two options. Either I could think of this as multiplication, or I could think of this as division. Let's see how that works. X approaches infinity. This will approach infinity. That will approach 0. So the yellow is not working. If I look at this as a fraction, because over 1, natural log of x over 1, this is infinity over infinity. That benefits me a lot more. So I could go for L'Hopital right away. Derivative of the top is natural log of 2 is a constant. That's 1 over x. Derivative of the bottom is 1 over x. Those undo each other. And you're left with natural log of y equal. Limit of a constant is the constant. So what would y equal? E to the natural log of 2, which is 2 in this case. And that takes care of it. That's pretty much it. '64 next. I have the same option. Again, I could say that's e to the natural log of x to the e, because that's infinity. And as x approaches infinity, that approaches 0. Or I could say, you know what, natural log of y equals, and I could jump straight to it. Limit as x approaches infinity of natural log of x to the e to the negative x. And natural log of y equal, and this is a trick that you could use in any science class. Any class you look at, and you are dealing with a power, and you can't seem to go anywhere, log both sides. That's the power of logs. Now this is 0, that's infinity. So this is an easy fix since we never ever touch logs, ever, or inverse trig functions. So natural log of y will equal by L'Hopital limit as x approaches infinity 1 over x over e to the x. And I could say natural log of y equal limit as x approaches infinity. This is 1 over x e to the x. That approaches 0. And y will equal e to the 0, which is 1. Same thing with number 66. If I put a 1 in there, 2 minus 1 is 1, and tan of pi over 2 is infinity. 1 to the infinity. Again, I could say let y equal this, and natural log of y equals natural log of the, I could skip a step and say the limit as x approaches 1 of natural log of 2 minus x to the tangent of pi x over 2. Natural log of y equals the limit as x approaches 1, one of the properties of logs, that is tangent of pi over 2x times natural log of 2 minus x. As x approaches 1, tan of pi over 2 is infinity, or negative infinity, it doesn't matter. And this is 0, natural log of 1. So that good news, if it's a log, whether I'm integrating or whether I am taking a limit, I never touch a log, so I know exactly what to do in this case. 1 over tangent is the cotangent, and if I take, this is now 0 and this is 0, natural log of y equal by L'Hopital limit as x approaches 1, derivative of the top 1 over 2 minus x times negative 1, derivative of cotangent is negative cosecant of pi over 2x times pi over 2, natural log of y equal the limit as x approaches 1 of, let's see how this works, the negatives cancel out, 2 over pi times 1 over 2 minus x times, and the secant comes out as a sine of pi over 2x. And if I throw 1 in, I will get 2 over pi. The sine of pi over 2 is a 1. 2 minus 1 is 1. That's 2 over pi. So I could say here y equal e to the 2 over pi. That would be my answer. And this is a star problem, number 60. If I look at this problem, this looks pretty much like a compounded interest. If I let x approaches infinity, this will approach 0. That will be 1 to the infinity. This is something you really want to pay attention to. So if I say natural log of y equals the limit as x approaches infinity of natural log of 1 plus a over x raised to the bx. Property of logs, natural log of y equal the limit as x approaches infinity of bx, natural log of 1 plus a over x. And we know the drill. We never touch a log. This is infinity times 0. Natural log of 1 plus a over x divided by 1 over bx. So natural log of y equal by L'Hopital, because now this is 0 over 0. Limit as x approaches infinity. This will be 1 over 1 plus a over x times negative a over x squared. Derivative of this will be 1 over b, you leave it alone, times negative 1 over x squared. So the negatives become a positives, those cancel out. Natural log of y will equal the limit as x approaches infinity of a b over 1 plus a over x. As x approaches infinity, this will approach 0. And I'm left with natural log of y equaling ab over 1, and y would equal e to the ab. Something I want you to really look closely at. If I was to look at this as 1 plus a over x raised to the x all raised to the b. And if I take the limit as x approaches infinity, I'm going to show what this part equal, because that's something that's going to come up all throughout this class for us. I'll come back to that and apply it right here. So here, I'm going to look at this. This is compounded interest. N is the number of years. N is the number of compounds per year. N equal 1, that means 1 year. Semi-annually, N equal 2. Quarterly, N equal 4. Interest rate, principal, and the amount after a given time. If I look at 1 plus r to the n raised to the n, and I call this y equal, and I want to take the limit as n approaches infinity of that. That would be y equal, this is 1 to the infinity. So when I take natural log of both sides, I'm really looking at natural log of 1 plus r over n to the n. This is natural log of y equal, by properties of logs, limit as n approaches infinity of n natural log of 1 plus r over n. This is infinity times 0. So natural log of 1 would be, actually, as n approaches infinity, that was 0 to the infinity. My mistake. Natural log of 1 is 0. So this is the limit as n approaches infinity. We never touch a log, whether I'm integrating, which is the next chapter, or I'm taking a limit. And I notice here that this is now 0 over 0. Natural log of y equal, by L'Hopital, limit as n approaches infinity. Derivative of the top, 1 over 1 plus r over n, times negative r over n squared. Derivative of 1 over r is negative 1 over n squared. The negatives cancel out. The n squared cancels out. And I'm looking at the limit as n approaches infinity of 1 over 1 plus r over n times r. As n approaches infinity, that's a 0. I'm getting an r. And that means y equals e to the r. And if I come up here and say, you know what? This is actually e to the r. So this is p times e to the r raised to the t, and that is p e to the rt. So the limit as n approaches infinity of 1 plus, if the denominator and the power are reaching infinity, this is simply e to the a. You could use that at any given time, and that's simply e to the ab. If I say show that on the exam, you have to do the whole work, but if you could see it, you'll proceed like this is an actual problem in section 11.6. I'm taking the limit as n approaches infinity. Instead of using L'Hopital, and that takes you a while, if you can think of this as n plus 1 over n to the negative n, and that is the limit as n approaches infinity. N over n is 1 plus 1 over n raised to the n, all raised to the negative 1. Properties of powers. This right here will be e to the 1 raised to the negative 1, and that is simply e to the negative 1, which is 1 over e. Something that's going to come up a lot for us. Something that worth noting. Last problem I want to look at. As x approaches infinity, we know that this is going to be a 2 over 2, which is 1. And that's going to be infinity. So there's a power. Again, in any science class, you are stuck with a power. You're not sure what to do. Most likely logs are the way to go, because those are the only functions in math up till now that can manipulate power. So properties of logs. Natural log of y equals the limit as x approaches infinity of 2x plus 1, natural log of 2x minus 3 over 2x plus 5. Now this is infinity times, and this is natural log of 1, which is 0. Again, whether you are integrating or taking a limit and there's a log involved, you really do not move a log. That's unwise. And this is 1 over, or 2x plus 1 to the negative 1. Now this is 0 over 0. Now I could apply L'Hopital, limit as x approaches infinity. Oops. I could say natural log of y equal the limit as x approaches infinity, and derivative of the top is 1 over 2x minus 3. So 1 over a fraction is the reciprocal of the fraction, times the derivative of the inside. Derivative of the top is 2 times 2x plus 5. Derivative of the bottom is 2 times the top, all over the bottom squared. I don't know why I'm squishing this. There. All over, and the derivative of that, bring the power down, subtract 1 from the power, times a 2. And natural log of y will equal the limit as x approaches infinity. And here, I know this cancels one of those. And I'm looking at, let's see, that's a negative 2, of course. That would be negative. And this is going to move up. That's 2x plus 1 squared times, and it's going to be over 2x minus 3. This will be 4x plus 10 minus 4x minus 6 all over 2x plus 5. Those cancel out, and I'm looking at natural log of y equal the limit as x approaches infinity. And let's see how this works. If I look at this, this is merely a 4. So I have 2x minus 3, 2x plus 5. If I could apply L'Hopital, I could divide by the highest power term of the denominator, which is x. So that's 2 minus 3 over x. And that is 2 plus 5 over x. And that is 2 plus 1 over x squared. That will approach 0, 0, and 0, and we'll get negative 2 over 4, which is negative 1/2. So y would equal e to the negative 1/2, and that would be my answer. And there's my homework. That's the second half of this section.